Hey, this is question 1A. I'm just looking at your questions that I thought I would go through. And 1A is the silver electrode in a silver ion solution and a cadmium electrode in a cadmium ion solution. Right, so I'm going to draw my two half cells. That's a beaker for one half cell. There's a beaker for the other half cell. And I'll put in an electrode. And so we'll just have this as my cadmium, and the electrode that's resting in this solution will be my silver. All right, I'm going to connect these two half cells by a salt bridge. I'm going to plug the salt bridge with some cotton batting to prevent the salts in the solution in the salt bridge from just falling out. And there's a solution of cadmium ions in this half cell, and for this half cell we'll have there's a solution of silver ions. Connecting the two electrodes, and there's a voltmeter there. All right, now I can label the anode and the cathode here based on the strongest oxidizing agent and the strongest reducing agent. The strongest oxidizing agent are the silver ions, and so electrons are actually going to be moving from this reducing agent, that is cadmium, and moving along our conducting wire and going toward the silver ions. And so the electron flow is going to be this way. These are my electrons. And the oxidizing agent is where the cathode electrode is. And the reducing agent, where electrons are leaving, is going to be the anode. All right, so let's see. I've labeled the cathode, the anode, and the direction of electron flow. Now, the oxidizing agent is the agent that's responsible for collecting the electrons here that's coming over. And even though we label the electrode the cathode, the electrons are coming over because they're being attracted to the silver ions, which are the strongest oxidizing agent. So my silver ions is going to be my oxidizing agent, and the cadmium metal is my reducing agent. Okay, the direction of ion flow to or from the electrodes. Now, if electrons are leaving the cadmium metal, what's happening is the cadmium metal is leaving, causing the electrons to leave, and the cadmium ions are leaching off into the, sloughing off into the system, increasing the concentration of cadmium ions in the solution here. Now, I'm just going to make up a couple of unreactive ions in my salt bridge. So let's say nitrate ions and potassium ions. Now, the ion flow in the salt bridge is going to be directed toward the side in order to balance charge. I'm going to have an increase in positive charge as cadmium ions increase in the solution here. Now, in order to counter that increase of positive charge, my nitrate ions are actually going to be flowing out and into this solution to balance the charge. The silver ions are being attracted to all the electrons that are actually coming into this electrode, and the silver ions then are going to attach themselves to those electrons on this electrode. So we're having a decrease in positive charge at the cathode here. So the potassium ions that I have in the salt bridge are actually going to be moving out. Pretty much answered the whole thing there. Now for question number 2, it says for each of the above voltaic cells, write out the cathode reaction, including the little degree sign means that that's the standard cell potential, or in this case half cell potential, and the anode, and then the net. Okay, well the half reaction at the cathode is this guy here, and it's a reduction half reaction. So I've got silver ions and combining with electrons to form silver metal. Now I've been putting the E degree sign here, I've been putting red underneath, meaning that that is the reduction half cell potential. I'll explain why in a moment. Okay, so this is a reduction half reaction, so my reduction cell potential for silver, I have to look it up in my data book, and it is 0.80 volts. Positive 0.80 volts. All right, anode is an oxidation half reaction where my solid cadmium is losing electrons to become cadmium ions. Reduction potential for cadmium is negative 0.40. Put it down here. Now, the thing is that I'll do it by, first of all, I'll put up the net reaction, and we'll see that I have to balance electrons, and so I'll end up with 2 silver ions, cadmium solid, producing cadmium ions, and 2 silver solid. Now the net cell potential here is going to be the difference between the anode and the cathode. Now, when I have no room to write it. I'll just put it up here. Let's have to take out this guy here. I've done this part of the reaction already. All right. To calculate the E net, it's going to be the reduction cell cell potential from the cathode minus the reduction cell potential of the anode. Now, this is the equation that they use in the book, and I have a little bit of a problem with it, but I want to be consistent with the book, and it does work quite well. Just a little bit of a subtraction thing going on here. Why do we have to subtract the two numbers? Well, the reason is like this. When you write out the reduction half reaction and you write out the reduction potential, you can just stick it all in one long row like this. But at the anode, oxidation is occurring. And so the half reaction that you put down is the oxidation half reaction. I would prefer to put down the oxidation potential, which is the same numeric value, just a different sign. So the oxidation potential for cadmium would be positive 0.40. So that when you add up the equation here, just as you add them up after you've balanced electrons, you add them up, you would then just add up the half cell potential for the reduction half reaction and the half cell potential for the oxidation half reaction. To me, that makes great sense. However, your book chooses not to do that, and instead they do this subtraction. Instead, the numbers that you copy out here are the ones derived from your data book. They are the reduction cell potentials for those half reactions. So even though I write out the oxidation half reaction, I've actually put in the reduction potential so that it sits comfortably in this equation here, and the equation is promoted in your textbook. So the reduction half reaction at the cathode is positive 0.80 volts, and I minus the reduction half potential at the anode, which is negative 0.40 volts. I mean, the answer comes out to be the same. It just makes sense to me to, when you're adding up the two equations, to add up the half cell potentials. But the book does it in two distinct processes. Add them up to get your net equation, and then subtract the anode from the cathode to get your cell, your E cell or your E net. All right, so this is positive 0.80 volts added to 0.40 volts, and the E net, or the E cell as your book likes to call it, becomes positive 1.20 volts. Now this value, positive, indicating that it's a spontaneous reaction, and voltaic cells have a spontaneous reaction.